add encoding to your project report as well. And then you have to add the references, like I mentioned last time. Okay, use a formal format for the references, please. Personally, I prefer to use IEEE format, okay? But that's not the only format you can have. I prefer you to use IEEE. Well, personally, I prefer IEEE format, IEEE format. Okay? That's for the VIP developer. Okay, again, if you have any questions regarding the report, final report, come to me. Okay, come to me. Let me know what happened. Okay, all right. Okay, let's go to the example. Okay, in this example, suppose we are given an input signal, okay, XLP. This is the input signal. And then you use on the screen. Okay, so we are given the input signal XLT, and also we have transfer function. We have a system. This system is an ideal responsibility. And then the output is YLT, right? Okay, and what is the frequency response? What's the relationship? Omega C or something? Yeah, omega C. Let me follow the notation. Okay, now the idea of this example simply tells you that if I have an XLT plus signal, and that signal can be represented by using the is N. This is the minus 1. Right? N over minus 1. So you can see how the notation given N plus 1. This is N plus 1. This is N plus 1 times omega 0. And this is N times omega 0. And similarly, in the negative frequency, this is N omega 0. This is N plus 1 omega 0. Alright, now suppose the Fourier transform of the input signal x of t can be written as the impulse train. 2 times pi times the Fourier coefficient x of k times the delta function omega minus k times omega sub 0. So which means if you look at the spectrum, it's going to be like this. Okay, that's omega 0 equals 0, and then usually the higher the frequency, the amplitude, the smaller the amplitude usually, okay, for regular signals. Okay, now if this signal goes through a low-pass filter, and this is the ideal low-pass filter, H of S, we replace this by J omega. So this will be the frequency response of the low-pass filter. So as you can see, when the frequency is higher than the cutoff, this is the cutoff frequency, then the amplitude becomes 0. So for those pitch, okay, for those pitch, frequency higher than the cutoff frequency, the signal will be attenuated. So after going through so this is the x of omega, right? So if I draw the spectrum, this will be N plus 1, omega 0, and nothing here. Okay, so see right here. And then this is negative. N plus 1 omega 0. So for those which, okay, for those which frequency is higher than the cutoff frequency, the amplitude reduced to 0. Okay, what attenuated or will filter out by the low pass filter, supposed ideally. Okay? So this is the effect of going through this ideal low pass filter. But again, if you look at the first thing first. So that's why you can see that once it goes through the low pass filter, this is the output, frequency response of the output. The summation is going from negative n to positive n because those which higher than the cutoff frequency, they are filtered out, they are attenuated, so they are zero. The amplitude becomes zero. So we only keep the term within the cutoff frequencies. Okay? But then the problem is, if you look at the time domain response, if you look at the time domain response of the low pass filter, it is done forward. Okay, this is the time axis. These are the time in the future you need. Okay? So this cannot be the ideal filter. Ideal low pass filter cannot be used in real time for signal processing, but it does can be used for the data process offline. Okay, offline process is fine. We don't need to process the time right away. Okay, we can collect all the data and go to the lab and then reprocess the entire data set. So this can only be used for the offline processing. Okay, but cannot be used in a real-time process. That's a problem. I'm not sure if we have time to go through this small program. Okay, do you want to run the program? Try this program? Just use about 10 minutes. Okay, it's a very small program. Okay? Try this one. Okay, try this one. This is for plotting the sync function, this one. And this is for the sync function, definition for the sync function. Okay, then I'm going to ask you, what am I doing here? Set of F data. Can anyone tell me what's that? Okay, try to run the program first and see what happens.
This species is one of the
format.
Now later on you are going to see the sync function very often. It's an important function. This function is very important. You are going to see this function in many different applications.
So I should use X instead of U. This should be X. So I use X. Okay. Sorry. Replace this by x, sync of x. So that can be consistent. Okay? It's a very small function. So just want you to be familiar with the sync function. Okay? So the least space means we define the time interval from -5 to +5, and I divide interval into 1,000 intervals. 1,000 intervals. Sometimes I prefer to use 1,000 into 1. It doesn't make too much difference. Okay? Just my personal preference. So again, this small program just want you to be familiar with what is the sync function, okay, and how it looks like. So your curve will be very much similar to this one. But there's a peak in the middle at t equals 0, and then some ripples. Okay, again, I need you to tell me what I did here is for what purpose. Can anyone tell me what is the purpose for doing this set F data? Internal plot format SVG. SVG is one of the format of graph, right? Of a figure. One of the format of the figure. Usually we use PNG or JPG. And another one is SVG. So what is the purpose of using this command? Set F data. Did anyone find that? Could you help this command, set F data? Okay, some of you may use the ChatGPT, right? You may want to ask ChatGPT what is a command set F data used for? What is the purpose of using this command? Actually, without this command, we still can run the following command, that's fine. Okay, but what did I put there is for what purpose? Sorry, Freddie? Yes, correct. Okay, because I want to export that figure. I'm using the SVG format. Okay? Because later on you may want to use the graph, use a figure you generated, right, for your report. Then you need to determine what is the format you need for the graph or figure. Okay? But actually you also can export your figure manually, that's fine, but better to put it automatic eventually. Okay? Alright, okay, one more thing I haven't mentioned is the output. The output, okay? This x of omega, okay, that's the input. But the output y is in a frequency domain, or in the s domain, is equal to input times the transfer function h of j omega. Okay? So you need to multiply this guy by h of j omega. By h of j omega. But once you multiply this h of j omega, then you can see that all the frequencies higher than the cutoff frequency are attenuated, are gone. So only the finite terms from negative n to positive n are left. Okay? Let me repeat what I said. Originally, your signal has infinite frequencies. A from negative infinity to positive infinity. But once you go through the low pass filter, again, one more time. This is the low pass filter. Okay? Low pass filter. So all the frequency components beyond the cutoff frequency will be cut off, will be attenuated, will be filtered out. So the amplitude of the frequency, the amplitude of the frequency higher than the cutoff frequency becomes zero. Okay? Well, by the way, the amplitude is 1. This is 1. Okay, so that's why you don't see anything here. But you can see that this should be 1. Theoretically, you should put 1 here. 1, you should put 1 over here. Okay? 1 times 2 pi times x k times the filter function. But the important thing is you can see that now the terms in the summation are finite from negative n to positive n, because the frequencies higher than higher than omega c now are zero. Now are gone due to the filter, due to the low pass filter. Okay? Alright, so that's the idea of pass filter. Okay? Are you done here? Have you finished, everyone? Okay? Alright, so now let's conclude the chapter and move to another chapter now. Okay? Sampling process. Okay, allow me to skip to the sampling process. Application of Laplace analysis and control. We have another course, automatic control. In the course, in automatic control, this application will be studied extensively. Okay, so I'm not going to touch this chapter 6. So I'm going to skip chapter 6. Because we have another class, automatic control. In that class, we are going to consider this in much more detail. Okay? Next semester, actually. In next semester, we have another class for this. So I'm not going to consider chapter 6 this topic. So let's move to the chapter 8. Sampling theory. This is very important. Now, up to this moment, most of the cases we are considering is for continuous signal. But actually, when you try to implement the technique you learn from any courses, okay, including this one, will be in the discrete system, in the discrete domain, discrete time domain. That is because you want to use computer. You want to use the power of computer to help you to solve the problem, to analyze the data. Okay? So let's go through this first one more time. Okay, now look at this figure here. Suppose we are given a continuous signal like this. This is a sinusoidal signal. Sinusoidal signal. The sine of 2 pi times 100 times t. This is the continuous signal. And it goes through C to D. This means continuous signal to digital signal, C to D. Okay, continuous signal. X of T to digital signal or discrete signal, X of N. So what does that supposed to mean? It means we are going to sample. We are going to sample the signal at every sampling time. At every sampling time. So you can see that at every sampling time we have a data with a dot, right? With a dot. So that is we take sample at the instant. So we take. Let me zoom in a little bit. Okay, so at one sampling time, we take data. 2 sampling time, we take data. 3 sampling time, we take another data, and so on and so forth. Okay, so you can see that for this one, the sampling frequency is 2K hertz, 2000 hertz. So that means we take 2000 points in 1 second. So the sampling time is 0.0005 seconds. 0.0005 seconds. Okay, but now if we choose a slower sampling frequency, this becomes 500 hertz. 500 hertz. And then you can see that this is the sample signal. Sample signal. So when the sampling time becomes bigger, the data points you will receive in interval become bigger. The data points you receive will be not so much like the original signal, right? Not so much resemble the original signal. And actually there's a catch, which is very important later on we are going to consider. What will be the maximum sampling time or sampling interval allowed? What is the maximum sampling interval allowed for taking the signal? Okay, that is the issue we are going to consider, which is extremely important. Okay? Now, mathematically or symbolically, we model the process. It will be late. The sampling process we have just mentioned is modeled by the following mathematical model. We have a continuous signal. Hopefully you can read it. Maybe I have to re-put this figure. Okay, this is the continuous signal. Continuous signal. And then go through a sampler. Okay? This sampler is modeled by impulse trend. Impulse trend. Okay, for a very good reason. But we are not going to go through that. So please just assume it is correct. Okay? So again, the continuous signal go through an impulse trend. What does that supposed to mean? That means the output will be the product of these two signals. Okay? So the output will become this one. Okay, so at the sampling time, we have an impulse. We have an impulse. We have an impulse. Okay? But then we have to convert the impulse to samples. So it becomes a product. The final number. And then later on we are going to confine this guy and also this guy. Okay, but for the moment, and then split the process one more time. We modeled the sampling process by using an impulse trend. So we have an input signal, which is a continuous signal, and then go through this impulse trend. The output will be the product of this continuous signal and the impulse trend. So this is the output after going through the impulse trend. Okay? And then we also have to convert it to discrete signal. So it becomes finite. Okay, well, that's the process. Again, please take this process for the moment. We have a good reason for doing this. Okay, someone invented this. It's very clear. Okay, so in the book, you can see this figure. Okay, that's the same person. We have a continuous signal, and then go through a sample. We take samples at every sampling time Ts. And those samples, those sampling process is modeled by an impulse track. Okay, after going through the impulse track, this is the sample signal. For the moment, those are impulse. Okay? Now, since this impulse track, this is the impulse track. It can be written as the summation of those delta functions with a shift, n times Ts shift. Since this function is a periodic function, right? Because if you shift this function to the right or to the left by t sub s second, it remains the same. So it is a periodic function. So I can represent this function by Fourier transform, Fourier series expansion. Okay, so I can let me erase on the screen. I forgot that one. So this is the chapter 8. Sampling theory. Okay, this all sample. Okay, now this guy, the sampling process, now it's modeled by N Ts, okay? Okay, Ts is time. And this is the periodic function. So it is a periodic function is, well, then I'm able to convert it to frequency domain. C sub K, then that's fine. And then E to the K times omega 0. Okay? Omega rotation. Omega is came from negative infinity to positive infinity. Okay? And then for the moment, let me use my notation. Let me follow the notation of the book. And then we can prove that the CK is 1 over the sampling Ts. And I think I've attached the proof. Here. Okay, so let me show you that. Oh, I call it dk, sorry. In my notes, I call it dk. Sorry about this. Let's call it dk. dk, okay? Okay, and then the sample signal is simply x of t, the input signal, times the impulse check. A direct product, okay? Direct product. So this can be written as x of t times the sum. And the minus times t. Is the interval, the period, sorry, is. Okay, yeah, let me follow that. Then, okay, we put the x of t into the summation. Because originally, this is a unit sum. Okay, we'll show you this next page. Okay, so this is equal to so e minus 2 e to the j minus 2 and then minus times p and then e minus 1 e to the j negative minus times p and then e sub 0 that's the image series. Okay? Now, if I multiply this entire image series by the function, so I just multiply each term by the function and then sum up. Just a direct multiplication. Okay? Now, the problem is why the piece of k is 1 over ts. Where does that come from? So I have to show you that. Okay? Let me show you that here. Oh, by the way, there's a very interesting figure. This impulse train can be expressed as the summation of those complex exponential functions. And if you look at this a little bit deeper, you will see a very interesting result. Now, when the time t equals n times ts, okay, when the time, this t equals the multiple of sampling time, then this is equal to 1. Okay, each term is equal to 1. So every term now are collapsed or coincide on the positive real axis with magnitude 1. So the sum will become infinity. So that's why at the sampling instant, ts, negative ts, 0, 1 ts, 2 ts, n ts, their magnitude goes to infinity. And because you add 1 plus 1 plus 1 plus 1 plus 1 plus 1, there are infinite numbers of ones. So the summation is infinity, right? Okay, and then for those which t is now equal to ts, those summation of the complex exponential functions the sum of those infinite exponential functions turns out to be 0. Turns out summation to be 0. That's very interesting. So that's why in the time in between the sampling time, nothing here. Actually, that's a 0. Okay? Nothing here. Nothing here. Nothing here. But when the time equals the multiple of sampling time, it goes to infinity. Because you sum up all those terms, this is equal to 1. At t equals n times ts, then this complex exponential function is equal to 1 exactly. But you have infinite terms, infinite number of terms. So the summation goes to infinity. Goes to infinity, infinity, infinity. Okay? That's a very interesting result. And then in the next page, I will show you the reason. Okay, actually that's inner product of the function with the complex exponential. Okay, let's take a 10 minutes break and then come back on the popular break. Okay? Okay, so how do you find a coefficient? dk is simply an inner product of the delta function, the impulse strength. Okay, but this impulse strength actually is the delta function. Okay, let me speak. Rewind a little bit. Okay. Originally, we want to find the coefficient in the impulse strength, delta T sub s. Okay, this is the impulse strength. And since this impulse strength is a periodic function, it repeats. The period is T sub s second. Okay? Okay, so by using the Fourier series transformation, you can find coefficient by using the inner product between the negative 1/2 ts to positive 1/2 ts. That's one interval. Okay, that's over the one interval of the signal. One period, sorry. Let me say that one period, sorry. One period. Okay, but in this one period, you can say one more time. From here, sorry. From here to here. This would be from mine. I don't know what it is. Okay, anyway, so what I'm trying to say is, if integrate from only negative 1/2 ts to positive 1/2 ts, so this is the interval. Okay, from negative 1/2 ts to positive 1/2 ts. So this is the interval for the integration. So in this integration interval, there's only one impulse, which is delta of t, right? Okay, so so in this interval, from negative 1/2 ts to positive 1/2 ts, there's only one impulse, delta t. Okay, so you can replace this impulse strength by this single delta function. And since from the definition of delta function, the integral of this guy, of this function, is simply equal to delta of t times f of t, but only when t equals 0. Okay, only when this t equals 0, we have a function value. For the other t, the function value, the product of the function value, the product of delta t and this function becomes 0, or t is not equal to 0. So that's why we only leave 0 here. Okay? And the integral, let me erase the screen. And what is the integral? What is the integral? What is the value of this integration? Oops, sorry. Equals 1. Equal 1. How come? Because by definition, if you integrate the delta function, that's equal to 1, right? However, if you sketch the function, this delta function has non-zero value only at t equals 0. Okay? So actually, for this case, this is also equal to negative 1/2 ts to positive 1/2 ts. And that's equal to 1. Because for t equals For t equals 0, the function value is, you can imagine, goes to a very huge number. Other than t equals 0, the function value is 0, right? Sort of infinity, right? T equals 0. But t is not equal to 0. So it doesn't matter whether you integrate from negative infinity to positive infinity, or from negative 1/2 ts to positive 1/2 ts. The result is the same. This is equal to 1, and this is also equal to 1. The results are the same. Okay? Got it? All right. So we have 1/ts times the integral of the delta function, and which is 1. So that's equal to 1/ts. Okay? So now we have the important result over here. So the signal after the sample, x of s is the signal after the sample, is equal to the signal x of t continuous signal times impulse track. And then this also can be represented by this Fourier series extension. Okay? 1/ts times dimension x of t times e to the j k omega s times t. From k equals negative infinity to positive infinity. Now let me ask you, what is this? What is this? This is equal to this part. The summation of okay, look at this. This is equal to the summation of all the spectrum frequency response, or frequency response, or power spectrum of the signal with k times omega s shift. Okay, one more time. Okay, look at this one more time. Okay, one more. So we have the signal XLT as original signal, and the power spectrum is XL omega. And that's no issue. So XLT has the frequency response or power spectrum XL omega. Okay, one more time, let's go back to the, maybe it's better to go back to the previous slide. Okay, the power spectrum XL omega. Okay? Interesting. Okay, just want to remind you one more time. Okay, we have a signal XLT, which is a continuous signal. In general, it's not period or aperiod. We take Fourier transform of XLT, then we have the XL omega. This is the frequency response or power spectrum. We have to refer to call it frequency response. Okay, so this Fourier transform goes to this guy, XL omega. And by definition, it is the inner product of the original signal times the complex exponential function. Got it? Okay? Well, I keep that in your mind. Okay? So that's the Fourier transform of the signal. And then, and also we need the motion relation. So this series, but it's the same. If I multiply the signal by e to the j k omega 0 times t, okay, that's a modulation. Okay? So we multiply XLT by the sinusoidal function, precisely speaking. So this complex exponential function actually is a sinusoidal function. So if I multiply the signal in the time domain by a sinusoidal function with frequency k omega 0, then if I take the Fourier transform in the frequency domain, it has a shift. It has a shift, frequency shift. K times omega 0 frequency shift. Okay? Got it? Alright? I think I have proven something. Okay, forget it. I can see it right now. Okay, so let's go back to the summary. So one more time, if we look at the sample signal, that's the S of t, that is equal to x of t times the sinusoidal signal, the complex exponential function. Okay? And this frequency can from k equals negative infinity to positive infinity. So there are not infinite number of terms. Okay? And each frequency will have a frequency shift. X of t times e to the j k omega sub s. Then it has a frequency shift, k times omega sub s frequency shift in the frequency domain. And that k goes from negative infinity to positive infinity. So what does that tell us? This gives us a very important information. What's that? Which is originally the power spectrum of frequency response of the signal is this one. Okay? This is the frequency response of the x of t. But once it's sampled, once we take sample, so this becomes the sample signal. Then the corresponding frequency response becomes this one. Wow. We duplicate the frequencies and shift the frequencies. So one more time, this is very significant. Okay? I'm not sure if we figured this out in the very beginning. Originally, suppose this is the frequency response of the signal. This one. It's only one spike, okay, one pump. Let me call it pump. But once it goes through a sample, we have the sample signal. Now, if you look at the frequency response or power spectrum of the sample signal, it becomes this. We have multiple frequency response. We have so many pumps. Okay? And the distance between the pump is given by the sampling frequency, omega s. Okay? Now suppose this is 0, and this is omega s. One sampling frequency, two sampling frequency, three sampling frequency, and so on and so on. So that means we introduce or produce, let me say that, maybe use produce instead. We produce multiple frequency components. We start from only a single hump, but after the sample frequency, we have ending numbers of a frequency hump. Okay, this is the original, supposed. These are due to the sample, So mathematically, what is that supposed to mean? Means in the time domain, we have the signal, and it has a frequency response. Okay? And then we multiply this signal by this sample strength. Then in the frequency domain, we multiply this to the sample signal. Okay? This is multiplication in the time domain. Then in the frequency domain, it's a convolution. Right? Again, in the time domain, the output is equal to the product of the two functions. Then, in the frequency domain, the output is the convolution of the two functions in the frequency domain. So that's why we have so many. Actually, they are unwanted. We don't want that, but they just produce. They just coming out of the sampling process. Okay, but this has a problem, a very big issue. What's the issue? And let me use this one first. This video first. Suppose this is the previous response of the original signal, X of omega. Then after sampled signal, after sampling, the sampled signal has the previous response. That's right, you can see that, right? Because due to the sampling, so we produce many many previous response of the original signal. They are empty numbers. Okay, they are empty numbers. Now, if your interval, the interval between the two previous response is too small, then these two previous components, they can collapse, they can overlap. Okay, so if your sampling time is not small enough, you have the problem. We call it ADAC. So this figure is not so good. It's not good. Can you use this one? Yeah. Okay. Yeah, let me use this one again. So after taking a sample, we have the previous response like this. If the gap in between, the interval in between is too small, then you can imagine that these two previous responses, they can overlap. Okay, they can overlap. Okay, and that can be this one. Let me show you another. Yeah, this is one of the page. Okay, but we have another one. Like this. So this is the previous response of the original signal. Okay? Now, if your sampling interval is too small, too large, that means your sampling frequency is not fast enough. Then the second previous response will have an overlap with the original. Okay, so you can see that these two, they have an overlap over here. Okay, so the resulting amplitude, the resulting previous response will be this one. And you won't be able to tell the difference. This is due to the contribution from the original one or the contribution from this second previous response due to the sampling. That's called ADAC. That's called ADAC. Okay? Alright, let's go back to the video one more time. Okay. So you mentioned that this is the previous response of a signal, supposedly, right? This is kind of signal, sort of. And a certain sampling rate, here we use 10 Hertz for this problem. Then the previous response, they just sit right next together, okay? So there's no overlap, exactly no overlap over here, and no gap at all. This means we are able to use an ideal filter to filter out this component, okay, from negative 10 pi to positive 10 pi radian per second. And then we are able to use this signal to reconstruct the original signal. Okay, something else we are going to consider the number now. Okay, but then what happens is if we are using the time interval which is too big, that means the temporary frequency is too slow, then we may have the overlap. Okay, this is the, I just mentioned aliasing. And we are not able to reconstruct the signal again, no matter what. This is not good. Okay? The sampling rate is too small or too slow. Okay, so how do we analyze this mathematically? So maybe I have to write down the equation first. Okay? Just for illustration purpose. Yeah, here. Okay, omega s means sampling frequency. Omega s 2 pi over t sub s. Okay, t sub s is the sampling interval. Okay, now look at this figure. How do we avoid these two frequency response collapse? I need this, okay, this is the middle, 1/2 omega s. This is omega s. At every omega s, we have a reproduced frequency response. Okay, see it here? Due to the sampling. These are due to the sampling. Due to sampling. Okay, due to sampling. So the middle one is the original frequency response. All the others are due to the sampling process. Okay, to avoid aliasing, we do not want this frequency response to overlap with the original, right? So that means the middle frequency, omega s over 2, 1/2 omega s, should be greater than the maximum frequency of the original signal. Okay? All omega s bigger than 2 times omega s. This is the so-called Nyquist sampling theory. Okay, I explain this just by using a figure. Okay, there are some other rigorous procedure, okay, using the same function for that. So this is the Nyquist sampling. Here. Now this theory is very, very, very important in signal processing. This is one of the fundamental theory in signal processing. It tells you how small or how big your sampling interval can be used in order to avoid the aliasing phenomenon. Okay? So here I just use a figure to illustrate this result. But there is another mathematical procedure. Okay? So to avoid overlap, of two frequency response or two spectrums of frequency response. Okay? Two frequency responses. So we need this omega s. The sampling frequency should be greater than equals to 2 times omega max. Omega max is the maximum frequency of your frequency component in the original signal. But practically speaking, this is the theoretical number. Okay? Practically, we use omega s. Bigger than 10 times omega max in many of the cases. Okay? Just a rule of thumb. You can use smaller, you can use bigger, that's fine. But you have to know that if you use a faster sampling, or faster sampling or whatever, something similar to that, okay? This sampling device, if your sampling time is very, very fast, sampling response is very, very fast, then that means the cost is also very high. Okay? So for an engineer, you want to have a faster sampling process. You need your sampler to be fast enough to overcome unwanted phenomena. But in the meantime, you also have to consider what is the cost you are going to pay for that. Okay? Because faster means money. If you use a very fast sampler, that means you are going to pay lots of money for that. And another thing you have to think is, do you really need so fast sampling? Okay? Because if you are an engineer in a company, you want to develop a new product for your company, then the cost is one of the issues you have to consider. You don't want to invent a product which is so expensive, no customer is going to buy it, right? You have to use a device which has the lower cost, so that everyone can afford to the product, can afford to buy it. Okay? So there's a balance problem over there. Okay. All right, let me go Okay, that's called a continuous signal. Okay, but then we are now considering the sample signal. And one thing you have to consider is replace x of t by x of ts. Okay? Because actually, that's no big deal. And then we'll have to down here. Okay, so in the last hour we expressed the sample signal x of t by the product of signal x of t and impulse train. And that impulse train is the infinite sum of those delta functions, right? Okay, and also we can multiply, and we can put this x of t into the summation to multiply each delta function. And also this equals to x of ATS times the delta function e minus 1ts. How come? Why is that? Why is that? Why is that? Why I can do that? Why I can do that? Okay, let me give you 1 or 2 seconds to think about this. Why? Okay, you may be confused. Suppose this is the XRP. Just an example, okay? And then we have the impulse plane. Delta T minus n PS is equal to 0. T is not equal to n PS. Right? Okay? And then let me use infinity. This vector is not so precise. So T is equal to NPS. Okay, and precisely speaking, I have to write this. So maybe, okay, let me show you another thing here in this way. T, okay, and this is NPS. Let me use the rectangular
Approximation.
for the impulse. This is the same case.
This is NPS. Plus
1/2 delta, the use delta. Okay, and this is NPS minus 1/2 delta.
the function value is equal to 1/2.
So by using this notation, you have to redefine. So this function is equal to 1/2 for t is between NTS minus 1/2 delta and NTS plus 1/2 delta. And then equals 0 onwards. So you can see that the area actually is equal to 1. Okay, this is the rectangle approximation. Okay, now if I multiply this x of t times times this function. Just pick one of them. Just pick one of them. Let me skip that here. Okay, over here we have a delta function. We have an impulse. And the center is NPS. And this is NPS plus 1/2 delta. And this is NPS minus 1/2 delta. Okay? And this is x of t. This curve here is x of t. So what is the product? So this function, x of t times the delta function, equals this one. Okay, this is 0, 0, 0, 0, 0, 0, 0, 0, and then up to NTS. This is NTS. And then up to here. This is NTS plus 1/2 delta. And this is NTS minus 1/2 delta. Okay, but this time the function value is 1/delta, but times x of NTS. Right? Okay, so the product becomes so let me write this one here. Okay, so the product becomes 1/delta times x of NTS. When t is in the interval. And then 0 onwards. Okay? So that's why at every NTS, this x of t actually can be replaced by the function value at that sampling instant. So use this rectangular function to represent the delta function. I think it's much more clear. It's much more easier to understand why it can be written in this way. Okay, is that clear? So that's why we can replace it by using the x of NTS. Because we only care the function value at this point. Okay, anyway, the major issue we are concerning is this language sampling frequency. Okay? No matter how many theories you are going to learn or you have learned, in the signal processing, this is the fundamental theory you have to remember. This is the bottom line of the signal process. You have to know how fast or how slow your sampling can be. Okay? And then how do you determine your sampling rate theoretically? But practically, we want to maybe multiply it by 10 or smaller, up to you, okay? Depending on your application. Depending on your application. Okay, so again, your sampling frequency must be greater than, okay, I don't want to use the equal sampling. Must be greater than 2 times the maximum frequency of your signal, maximum frequency component of your signal. Okay? And that's called the negative sampling theory, the negative sampling rate. But for some cases, your signal is not band limited. If it is not band limited, they will want to consider this condition. You have to find your omega n. Okay? You have to determine which omega you are going to use to represent the maximum frequency. Then you have to compute in some sense the power, okay, the energy is about 99% of the total signal. Okay? Okay, there's an example. So let's go through this example next time. Okay? Alright. So any question here before we leave? I think this is new to everyone. Okay, so this is very important. And also, later on when you are going to process the signal, you have to consider the sampling rate. That's very, very fundamental and very, very important. Okay? Alright, any questions? One more time. Okay, then see you next time. Have a good evening and good weekend.